I think we're just about ready to get started. So good morning, everybody, and welcome to today's JKMRC Friday seminar for Friday the 16th of April. My name is Nathan Fox from the BRC unit of the University of Queensland. Welcome, everyone. Thanks for joining us. Hope you had a nice Easter break. Before we begin, on behalf of the SMI and the University of Queensland, who are based here in Brisbane, we'd first like to acknowledge the traditional owners on the land on which we meet today, and we pay our respects to their ancestors and to their descendants. It's a pleasure today to introduce today's speaker, Ray Koenig. Ray is the Technical Director for Carpentaria's Hawsons project. By way of background, I know Ray's going to give an introduction as well, but Ray holds a diploma in metallurgy from the School of Mines in Ballarat and a BSc Honours degree in metallurgy from the University of Melbourne. Ray has a background in magnetite processing and pelletisation, along with experience in large-scale project management and development. This includes research and development into high-temperature reduction of ilmenite. Along with being the Technical Director for Carpentaria's Hawsons project, Ray is also the Managing Director at Koenig Consulting Limited. The title of today's talk is Achieving Green Steel CO2 Emission Reductions, where Ray will explore the opportunities to economically reduce carbon dioxide emissions from the iron and steel industry using hydrogen. So it's going to be a very interesting and very topical talk today. Before we begin, for those of you online, if you can please type questions in the Q&A box on Zoom, and we'll get to those towards the end of the talk. But without further ado, Ray, it's over to you. Thank you.
Thank you, Nathan. Can you hear me all okay? Good. Okay, I guess a little bit of my background. I've been involved at the JKMRC here for many years. I worked in Mount Isa in the early 70s, and I worked with Alban Lynch. I was his gopher when he was doing his automated flotation work up in Mount Isa in #1 concentrator. And then worked with Bill Johnson on stream analysis up there. And I was actually disappointed in the design of the copper concentrator they built at Mount Isa, which was 3-stage crushing and rod mill and ball milling. So I actually went and worked down at Savajura, where they have two 32-foot diameter autogenous mills, which is what they eventually put in at Mount Isa. And that gave me a bit of a background in iron ore. How I come to have how I came to be involved in green steel was I've been doing some work for Carpentaria Resources, who have a very large magnetite resource 55 kilometres south west of Broken Hill, and it's probably about 10 billion tonnes of magnetite there. It's reasonably low grade in situ. It's only about 14 or 15% magnetite, but it's a bit of a metallurgical dream in that when you crush and grind it, it breaks around the grain boundaries, and you can make very high grade magnetite concentrate from it. So they're able to make 70% grade magnetites. And in order to obtain some customers for that material, we've been doing some work on the advantages of using higher grade iron ore, both for blast furnace iron and steel production and for direct reduction. And we've had talks with the Middle Eastern DRI producers and some of the steel works that are left in Europe. Okay, to get on with it. So what I thought I'd talk about was how much does the steel industry produce? A bit of a background, because I guess we're not all metallurgists here, so a bit of a background on how iron and steel are made. What are the lower alternative carbon processes? How much CO2 is produced in each of these processes, and what does it cost? Because if it costs far too much, then it's not going to be adopted. We've had some experience in direct reduction and using alternative iron production processes in West Australia, which haven't ended up very happily. And I'll cover that, and what are the future options, and perhaps a little bit on how that will affect the industry here in Queensland, our metallurgical coal industry. About 8% of the world's emissions of CO2 comes from the iron and steel industry. I think about 8% comes from making concrete and cement too. In Australia, the iron and steel production accounts for about 1.6% of our carbon dioxide emissions. Transport and agriculture being, and electricity generation being much bigger than the iron and steel industry. So that means that we contribute, or the iron and steel industry in Australia contributes to about 0.02% of the world's emissions. We have two iron making facilities in Australia, at Port Kembla and at Whyalla. Port Kembla, and we produce about 4.5 million tonnes of steel and steel products a year. The Chinese steel industry does produce quite a bit more. Their steel industry is estimated to produce 5.6% of the world's CO2 emissions. That's because they produce a lot of iron and steel. These figures are very variable. When you look them up on the web, there are figures all over the place, but this seems to be consensus on what the emissions are. Okay, now, where are the emissions made during the processing of iron ore into steel products? Now, the mining accounts for just less than 1% of the emissions produced when you're producing iron and steel. That surprised me. I thought all these big trucks running around, they'd be producing lots of CO2, but that's how the figures come out. Processing, I've looked at the heaviest processing, which is producing magnetite concentrate. So there's a lot of crushing and grinding. If it's direct shipping ore, it'd be less than that, but it's running at about 3% if you have to do a lot of crushing and grinding. That would apply to the magnetite plants in West Australia. There's 2 of those now. There's the Carrara operation that goes out of Geraldton, and the CITIC operation that goes out near Cape Lambert. The infrastructure was a fairly minor part of it, so that's involves the water used and the transport. Well, transport's a separate one. Sorry, transport is about 0.48%, which is a reasonable amount. 2% was involved in the pelletising. And I've assumed that these are pellets that we make. However, the blast furnace is overwhelmingly the biggest producer of the carbon dioxide. And steel, the steel side of it, where you're converting pig iron into steel, that is in fact 10%, over 10% of the CO2 produced. So that gives you a bit of an idea of where the CO2 emissions are coming from in the steel making chain. Okay. Hydrogen will reduce iron oxide. We don't have to use coal and carbon to produce iron. Carbon monoxide will reduce iron oxide to iron at about 700 degrees Celsius. And that's when iron oxide is still in the solid state. So that's how reductions are happening in the blast furnace. Hydrogen reduces iron oxide at about 1,000 degrees C. It might be a bit less. If you check with the LNM diagram, and I guess not too many would know what the LNM diagram is, but it shows what materials will reduce the iron oxides at different temperatures and pressures. As I said, both of these reductions happen in the solid state. So we don't have to make iron molten to have a reduction. The direct reduction process using hydrogen that has been used for years. It's Midre has been around for 30 years. There are commercial plants around the world now that are producing iron, direct reused iron, using hydrogen. Now that hydrogen is made in all cases by using natural gas, the reforming of natural gas. When you reform natural gas, you produce hydrogen and carbon dioxide. So you don't get much advantage in terms, if you use natural gas, of reducing the carbon dioxide emissions. You'll notice in the Middle East, that's where you've got lots of cheap natural gas. That's where a lot of the direct reduced iron is made. There is still a lot in India and around Asia. Latin America, there's some direct reduced iron produced. Eastern Europe, North America, I thought North America would have more direct reduction plants, but they're only about 5 million tonne a year. Africa and Western Europe. We did produce some in Australia in the Pilbara for a little while there at the HPI plant at Port Hedland. The iron making process, and since we've maybe got an audience of geologists here, this is probably handy. We start with either lump ore or fine ore, and we have to make it in a format that either suits the blast furnace process. The blast furnace process being, the blast furnace process going down this side. Traditionally, lump ore was fed into a blast furnace with coke. Now we either use a lump combined with sinter or pellets, and these make it into lumps. You have to be able to blow gases through the blast furnace, so it has to be porous, and so these have to go into the furnace as lumps. Then the iron that you produce in the blast furnace then goes into a steel making section. Most of the iron goes to steel. There's not a big demand for cast iron these days, which can be an alternative process. And steel is made either using an open hearth furnace, which I don't think there's too many of them around, or a basic oxygen furnace. The basic oxygen furnace really, it's a process where you blow oxygen into a molten bed of iron, and that reduces the carbon content of that iron so that you can make steel. Pig iron goes about 3 to 4% carbon, and normal structural steel is 0.1, 0.2% carbon. So that was Bessemer made the discovery of removing carbon from iron-made steel way back. Now, the alternative process is to use a direct reduction process in which you can use lump, but mostly pellets are used in the direct reduction process. The direct reduction process is using hydrogen, so you're using natural gas, or you can produce hydrogen from oil or even coal. It can be done in shaft kilns like the Midre and HYL process. It can be done in a rotary kiln, and it can be done in fluid beds. The HBI plant at Port Hedland used a fluid bed technology, which is probably one of the more difficult to control. The iron produced from these devices can then go into the electric arc furnace, or it can go into a basic oxygen furnace to make into steel. Recycled steel, I guess that can go straight to electric arc furnaces. Oh, I did it again. This is a schematic of the Midre process, and as I said, the key part of it is the gas reforming of natural gas. Natural gas is the main input, and you put your iron ore pellets into the shaft kiln and blow the reducing gas in. This is preheated. The reducing gas is preheated to about 1,000 degrees Celsius. It sounds scary. Hydrogen at 1,000 degrees is going to want to oxidize something. The product you get from the shaft kiln will oxidize. The pellets actually stay in the pellet shape, but they're porous. And because you've got fine iron particles in there, iron will burn as soon as it's exposed to air. So you either have to put it into your electric arc furnace straight away, or you briquette it so that you push the particles of iron together so they're less likely to react with oxygen. And so that's where the HBI part of it comes in, and you put it through a briquetting machine to produce a HBI product. You can't transport the reduced pellets long distances, or else they'll oxidize, and there have been some famous accidents in doing that. You can transport in hot transport systems, but it is difficult to handle fine iron, and that's what happened when BHP had a lot of difficulty in their fluid bed process, because the iron wants to reoxidize as soon as it hits air, of course. There's another process called the HYL process. It was developed by a European group, and it is very similar to that. But they have an interesting system here where they take the gases, off gases, and put it through a CO2 removal system. So this is almost set up for getting rid of CO2 as well. There is another process that has been around for about 10 years. It was developed by Kobe Steel and Midre in Japan and North America. And it uses a different technique. It's called the IT Mark III process. It's almost as if they did some experimentation and they got the temperatures wrong, and it accidentally produced a great product. What you do is you actually mix fine coal with iron oxide, fine iron oxide. You pelletize it and dry it, and then put it into a rotary half furnace. And that furnace is heated up to around 1,000 degrees. There's a dust recovery system associated with it. But what happens to the pellets of iron oxide and coal is they react together and get into a semi-molten state, so they come out as a globule of iron, which I think I've got a picture in the next slide. That's the sort of product you get out from it. It's easily transportable. It's not going to reoxidize again. And any slag that you've got, any impurities that are in the iron oxide, form a slag, and that can actually be easily separated because it seems to coalesce separate to the iron. It forms this stable product, so there's no need for the hot briquetting side of it. And it also allows a low-cost removal of slag. And you can use the same product handling systems that you do for iron ore. So you can put it into a big pile and have a bucket wheel reclaimer and your conveyors and load it onto ships. So I rather like this process. It's still got a bit of experimentation to be done, and Kobe Steel are working on it pretty seriously currently, I understand. Now, making hydrogen, you can make hydrogen two ways. You can use natural gas and reform it so you produce hydrogen and carbon dioxide in a gas reformer. You can also use it by electrolyzing water. The electrolysis of water has been known for years and years, but when I did my calculations on the cost of electrolyzing water, I found that it was about hydrogen produced by electrolyzing water cost 10 times as much as hydrogen produced by reforming gas. And then I looked at the CSIRO work that they've done recently, and that's about the case. If you use natural gas, and currently it's about $8 to $10 a gigajoule, hydrogen costs about $1.50 to $2 a kilogram to produce. If you use water electrolysis, the CSI Arena report is indicating about $19 a kilo. So it's confirmed my calculation about 10 times the cost. The CSIRO are saying that they may be able to get the price down to about half that, about $9 a kilo by 2030 with techniques that they're looking at. And there are some good techniques that they're looking at now for electrolyzing. There are catalytic reactions that they're looking at that could make it quite competitive. CSIRO also have a program where hydrogen is difficult to transport. Direct reduced iron is difficult to transport, so is hydrogen. Hydrogen is so small that it will leak through steel walls. So you can't really pipe hydrogen anywhere. And nobody tells you that when they tell you, oh, we're going to have this great hydrogen industry and we're going to fill our cars with hydrogen and drive them around. Hydrogen doesn't stand still, it will go through steel. You know, it is such a small molecule. So the CSIRO's solution to that was, well, we'll make it into ammonia, which is NH3. Now, and that's commonly done. That's to make ammonia. You make hydrogen and you react at pressure with nitrogen. And you can transport it long distance then, but then you've got to take the nitrogen away from the hydrogen. So I'm not quite sure that works. This is a graph that shows how much is produced by each of those iron production methods. And this is a blast furnace, which produces about 2,000 tons of 2,000 kilograms of CO2 per ton of steel. If you use high-grade pellets rather than the standard 58 to 62% iron ore, then you can make a reduction of about 10 to 15%. And I see that as low-hanging fruit. All the iron producers should be able to produce iron and steel using less CO2 than they're doing now, because they're using fairly low-grade iron ores. In the early days of the Pilbara, the grades were much higher, but they're not that high these days. If you use the IT Mark III process, where you're mixing carbon with fine iron ore, then it is less than the blast furnace, but it's still a fair bit. If you use the Midre process, it is quite a bit less than the blast furnace operation. This is a Midre process if you're using standard 62% iron ore grades. This is a Midre process if you're using high-grade pellets. So always high-grade iron ore, you produce less carbon dioxide. If you produce hydrogen using electrolysis of water and solar cells to produce that electrolysis, then you can reduce it to quite low figures. And these three figures here are showing what could be done. They're the sort of minimum areas of CO2 emissions that you could have if you used electrolytically produced hydrogen to produce iron oxide. And if you're able to capture the CO2 from IT Mark III, or use charcoal in the IT Mark III process, so a biofuel, then you could produce iron using the IT Mark III process. I wanted to check the figures, so I looked up the Kobelco report. Kobelco have done a lot of work on this, and this is straight from their report, and this is what they get for their carbon dioxide produced from the blast furnace, and this is what they consider 80% DRI use would give you, which is, the figures are about similar to mine. I always like to check my figures to make sure I'm at least in the right ballpark. Now the costs. I guess nobody has done the costs of producing iron in Australia before using these different processes. And so I set up my spreadsheet. I used the Japanese figures on and US steel production costs, but I combined them with Australian labour, consumable, and transport costs in Australia, that sort of thing. So for our blast furnace production, at Port Kembla, I haven't checked this because you can't get these figures off the web for Port Kembla, but they're running at about $550 per tonne of steel. With Midre, it would be a similar figure in Australia, and with High-L, was slightly cheaper. But Midre, if you were using PV hydrogen now, the cost would be, what, 3 times the cost of steel production now. In the future, if you could get your hydrogen or make your hydrogen for $9 a kilogram rather than $19 a kilogram, then that's what the cost would be. So it's still double the price of our current iron production costs. The IT Mark III, if we use charcoal from trees, which is a biofuel and is replaceable and renewable, then that's the sort of cost you'd be up for with IT Mark III. Now, there was a left field option that's gained popularity lately. I think even Twiggy Forrest has mentioned it. And that is we electrolyse iron oxide. And this is from their website, from Boston Metal's website. And this is a electrolysis cell that operates at 2000 degrees C. Now, I'm not, you can quote these numbers, but I don't think people understand how hot 2000 degrees C is. I've been involved in designing fused alumina and fused magnesia furnaces, and 2000 degrees is bloody hot. It's white hot, and I don't know what materials you could possibly make an anode out of. Graphite's going to oxidise, so it then becomes like an aluminium cell, of course, where you've got carbon is used in the anodes. But this is the picture that they have on their website. It has attracted quite a bit of research funding, and I'm I see it as a very left field option. But it does get mentioned quite a lot now. The World Steel Organisation, they have a plan for reducing their carbon dioxide emissions. They consider improving the efficiency of current operations. That's fair enough. That could include improving the iron ore grades, maximising the scrap recycling. Now in America, they've almost got to the point where they've reached the maximum of the amount of scrap they can recycle. Because when you recycle scrap, you can never sort out the stainless steel properly from the structural steels and that sort of thing. So you get contamination all the time. And that builds up the levels of chromium and nickel in the iron produced. So you need to have fresh iron ore that's got low chromium and nickel going into the process, into that recycling process to make it work properly. So that is not a bad idea, recycling. And then they talk about breakthrough technology in which they'll use hydrogen for reduction or carbon capture. So that's their plans for reducing carbon dioxide in the future. Australia's had a go at it. BHP built the HBI plant, which was a fine iron fluid bed operation at Port Hedland. I think it was about 15 years ago they started up. They had terrible trouble getting it going. I considered they hadn't done enough test work, and why would you choose to do a research project rather than just buy a Midre furnace and pelletize it and put it into it. But BHP decided they'd go with this fancy fluid bed. It's reported to have cost $6.5 billion US. It was eventually shut down because of maintenance and safety problems. It used natural gas, and there's about 12.8 gigajoules per tonne of HBI used, which is the carbon footprints are similar to the Midre process. So Rio had it was part of the agreement when BHP and Rio got the leases for their iron ore in the Pilbara, was that they had to do something to further process the iron ore. Rio's did it using a high smelt project, which was using lens technology. I guess it was a bit based on the Cyro smelt technology, and they could use cheap thermal coal in there. So that was their approach to it. They had a lot of difficulties in containment in a high temperature bath. The ISA smelt works pretty well on copper and lead, but it doesn't work when the temperature goes up more. The higher the temperature, the more difficult these processes are. And eventually Rio shut it down, but they sold the technology to a Chinese group, and apparently they're doing some more development work on it. So they may get it to work, and you can use cheaper coal. From my point of view, I've looked at, okay, what are the breakthroughs in achieving lower emissions and producing greener steel? I think it's use of conventional technology, Midre's high old technology, use of natural gas and maybe CO2 sequestration. I've suggested that if your photovoltaic cells only work, solar generation only happens when the sun's shining. So, and the direct reduction process is a continuous process. You have to run it day and night. So one of the suggestions I have made is that we You could use electrolysis of water during daylight hours, but always have a backup plan. You can store hydrogen for periods of time, and I would suggest that the way to go is to have a fairly large hydrogen storage and keep it topped up either using natural gas or water electrolysis. Now, the New South Wales government is actually putting together energy hubs in which they have normal thermal coal generation power. They have solar farms, and these hubs exist already, and they're looking at feeding Snowy 2 into it. Now, this may be a way where you can use off-peak power to generate hydrogen from water, and when it's not available, use natural gas. Now, strangely enough, NASA, in all their rocket launches, it's not true now, but they used to use hydrogen that was generated in Canada using hydropower, which is really cheap up in Canada, and then they'd ship it down in ships to Florida, which always surprised me. So it can be done. I rather like the IT Mark III process, where you're producing a product in one single step from iron ore to iron, and you're producing a product that's easily transported and handled. Now, Rob Leipson, in his column in The Australian a couple of months ago, suggested, why don't we use trees, biomass, to produce iron? And I thought, well, maybe I should look at that. And I've actually looked at it, and the next slide indicates the economics of it. Well, I showed you the economics back further. It was about, it's about 20% dearer than using coal. The molten oxide electrolysis, I'm not sure how that's going to work. Increasing our scrap recycling, of course, is always good. And all of these options are improved by using high-grade iron ore. Now, this should be a challenge to future metallurgists and those who are keen on mineral beneficiation to help Australia and the Pilbara to produce much better iron ore than they currently do. I looked at how practical it was to use charcoal in the IT Mark III process. Now, Australia actually exports 6.6 million tonnes of mostly hardwood chips currently, and it costs about $150 to $200 per tonne. This would give us about 2.2 million tonnes per annum of charcoal, and Australia currently produces about 4.5 million tonnes of steel. So we could mostly produce our steel using what we export in wood chips these days. So I thought that was interesting. Rob Leipson wasn't too far off the mark. and a final slide, I needed to look at how this is going to affect the coal industry in Queensland. We currently export about 275 million, probably 300 million tonne of coke and coal a year. That doesn't seem to have gone down. The Chinese still want our coke and coal. The world produced 1.8 billion tonnes of steel in 2019. 750 million tonne was from scrap. There was about 100 million tonnes from DRI, and 1140 of blast furnace produced steel. Australian coal miners produced about produced the coal for 30% of the world's blast furnace steel. Steel is at least likely to, blast furnaces are not going to go away. They're going to be around for a long time because of the costs. And because if you build a steel plant, it is a very expensive capital cost. So it's unlikely that there are going to be any big changes in iron and steel production over the next 10 years. So I think our coal miners are safe for another 10 years at any rate. And that's where I'd like to conclude, and it's open for questions.
Well, thanks very much, Ray. I think that was a really interesting insight for the coal industry in the next 10 years, certainly, but for the iron ore process in general, so thank you. Do we have any questions from the room, or Rick, any questions online? Do you want, I can go to Martin first and come back to you. Okay.
Hi, I'd seen tentatively that you could directly use solar power to reach temperatures that would. I'll start again. Yeah, in concentrated solar thermal energy generation, you just reflect the sun onto an area to generate very high temperatures and then use that to generate electricity. I had seen a couple of times claims that they could now reach temperatures that would be enough for a blast furnace using this method. Is that true, or is that still a bit of a pipe dream?
Sorry, I'm not understanding the question.
I'll ask you at coffee. That's okay. Thanks.
Thanks.
Sorry. Oh, yeah. Oh, you can melt iron. Yeah, you can melt iron. You can do that, yeah. Yeah. The reflected ones, the reflected solar systems do. I'm not in the camera, I don't think. The reflected, the question is, can you use solar reflected systems to melt iron oxide, I guess. And yes, you could do that. I'm not sure if you could get to the temperature. Currently, they're looking at using sodium, molten sodium, as a heated medium, and then using that to produce steam, to produce electricity. And that works. I've worked on a project where we used liquid sodium, and liquid sodium is a great heat transfer medium. It's a metal, and it's conductive, and it's a liquid, and it's convective. So it's got the same density as water to pump around, and it doesn't corrode steel. So great thing. But we're getting off the track a bit, aren't we? Sorry, next question. So it does work.
Two questions quickly. Not only do I steal Rick's spot, but I also ask two questions. So the first one is, you put up the prices of steel making using various processes in Australia. Do you have an idea of how those prices compare to Asian manufacturer, Asian steel makers in India or US steel makers or whatever? That was the first question. And the second one is, there's been a lot of talk in the European Union about reducing carbon intensity of steel making, but the focus has been, as far as I can tell, and I'm not a steel guy, the focus has been very much on reducing the energy required, the input energy, as opposed to the carbon produced in the reduction. Could you give me your impression of how those two split? Are there more gains to be made by using renewables, as Martin suggests, to heat the stuff up relative, or are there more gains to be made in the reduction process in terms of reducing the carbon dioxide?
Okay. So the first question was on the cost in Australia compared to other places?
Yeah.
Okay. It's cheaper to make steel in the US. Gas prices in the US are a third the cost of gas prices in Australia. And that's probably the chief driver of that. Labour costs are cheaper in America as well. I would think Middle Eastern direct reduced iron is probably the lowest cost, because they don't pay very much for their natural gas either, and they're producing their hydrogen from natural gas. Europe, I would think, would be fairly expensive. So that's a rough comparison. But China obviously is the cheapest of all because they've got such big plants and they've got scale there. But they can always benefit from a high-grade iron ore. Okay. Oh, what was the second question about?
The second one is that are there more gains to be made in terms of carbon dioxide energy required to heat this thing up, or if using something else to reduce?
Oh, okay. Well, heating it up, the heating up is normally done with waste heat in the iron making process. You know, a blast furnace, the high temperature zone is down the bottom, and as the feed goes in, it gets heated by the off gases. So there's already a regeneration of that heat. And of course, in blast furnace operations, they use copper stoves to actually heat the gases they're putting into the blast furnace. So the gases go in hot through the recycled copper furnaces. I'm not sure that heating using solar just to heat it up will give you too much of an advantage, because there is that regeneration. The Midre process, for example, is another shaft kiln. Shaft kilns are amazingly efficient. I worked on the magnesia project, QMAG, up at Rockhampton, and they have a shaft kiln there that fuses briquettes of magnesia at 2,300 degrees Celsius. Now, you can touch the briquettes as they go into the shaft kiln, and you can touch the product going out of the shaft kiln. And that stuff has been at 2,300 degrees. So shaft kilns are amazingly efficient if they work properly. So I'm not sure that any solar heating of it would be that helpful. More questions?
More questions. We've got a lot of questions online, actually. So I'm going to ask one of the first online questions, and I'm going to ask my own question. So the question, this is from an anonymous attendee: how do you add the carbon into the steel in the Midre process with hydrogen?
Oh, okay. Oh, yeah. That's good point. I'm not sure, actually. Obviously, on the IT Mark III and the blast furnace, the carbon gets in via the coal that's been used. I did know the answer, but I've forgotten, damn it. It's not high. It doesn't produce, the DRI produced has got a low carbon content, and perhaps that's an advantage in going to an electric furnace. But there's always some carbon around those operations. So yeah, if you've got an email address there, I'll get back to it.
Yeah, there'll be a record of all the questions. So, okay. And my question is a really dumb one, and that is, I don't know if you covered this, but why is it so much more expensive to use solar power? Is it just the capex for putting all the panels in, or why is the cost so high?
It's all the capital cost involved. Yeah, it is. Well, it's quite a big area that you have to. These are big. Well, that's a big electrical consumer. So it's sort of like shorting two wires in water, isn't it? It's a big consumer. Yeah, and so the solar field you require is huge. You can use wind, of course. You can use any form of electrical generation there. But yeah, it is more expensive. Now, I don't know whether using the reflective solar would make it cheaper or not, but yeah.
And sorry, I've hijacked your. Well, while I've got the mic, Marcin had a big long question that I didn't think it would be very good for me to read, so I promoted him to a panelist instead, and now he's going to ask his question hopefully online.
Okay. Thanks, Rick. Can you hear me okay?
Yep. Just speak up a little bit. It's a little bit quiet.
Okay, sure. Great presentation, Ray. I think my question was your early pie graph showed, the less than 1% or so of the total energy goes into is used in mining compared to the blast furnace, and about 3% in processing. Do you know if that data uses electric energy at the end of the electrical energy, or does it calculate the electrical energy based on the fuel used in the electrical energy? So does it take into account the generation losses?
Yeah, I see what you're saying. Well, when you make oxygen for the basic oxygen furnace, you use a lot of electricity to compress air and make the oxygen. Yeah, that electricity would be just from the grid, so it's going to be what is on the grid, and I would say it's from thermal energy.
Yeah, it'd be interesting to see what that would look like if you used electric energy that's generated from renewable sources. I also had a comment on the discussion regarding solar heat and solar thermal for smelting. It actually was trialed, and there was a research team in UK and Europe doing work on that in the early 2000s, and they had some success. I can't remember the name of the professor driving that, but the problems they had was with stability and maintaining temperature at the right levels with solar alone. I don't know where the status of that is at the moment.
No, I haven't read up on that either, I'm afraid. Yeah.
Thanks, Rick.
Yeah, as I said, preheating in a blast furnace is pretty good. They've got the blast furnace process, having worked on it for a couple of centuries, they've got the process pretty efficient. Yeah.
Okay, so thanks, Kay. I have a question is now the hydrogen generated from the natural gas reforming gas is referred as the green hydrogen. So it's not like it's a green hydrogen, not a green hydrogen. So what's your opinion of how long will it take? Do you think it will take to change to the 100% hydrogen reduction?
Oh, okay.
Yeah.
I think there's a potential to make hydrogen by the electrolysis of water fairly cheaply because of this catalytic type work they're doing currently. And there's an interesting paper that I read just a couple of days ago that shows you can improve the efficiency of the electricity in generating hydrogen up to 100 times. So if you could do that, then the direct reduction processes are there. They're well established. So if you can make hydrogen cheaply, then you can make significant reductions in carbon dioxide emissions, for making iron itself. Yeah.
So how long do you expect will happen then?
Oh,
within 10 years or?
Well, the CSIRO said 10 years to reduce the price of making it by half. I think it might come a little bit quicker than that, actually.
Okay.
Yes.
Martin, you're back for more. We'll go to Tim first and then back to Martin.
Thanks, Ray. That was a really interesting talk. This is stuff that's important that we don't often think about. A simple question on the production of hydrogen by electrolysis of water. How much water do you need? Would the supply of water be a problem? In other words, would you need to put these plants on the coast, for example?
I don't know. That's a fairly simple chemical calculation to make, isn't it? I guess for each kilogram of water you need I don't know. I'd have to sit and work it out. I can't work it out in my head. Hydrogen's about a tenth of the volume or mass of water, isn't it? 16th. So you need 16 kilograms of water to produce 1 kilogram of hydrogen. So yeah, it's probably a lot of water. Yeah, and we are talking about I did work out how many tons of hydrogen you need a year. I think you need to make 10 million tons of steel, or no, to make 10 million tons of steel, you need about 10,000 tons of hydrogen or something like that. So you're right, it is a big figure. You need to do it in a wet area. So maybe arid Australia is not the place to be doing it. Yeah.
You've got the sun in one place and the water in another, and
Yeah.
you might have a problem, I think.
Yeah,
Can I ask one more question?
Yeah.
A lot of the technologies that people are looking at for driving down the production of CO2 in all industries is driven increasingly by political decision making by governments and organisations like the EU. Now, we're all going to be driving electric cars in 10 years because the EU's told us to. It's quite simple. They're just saying we're not going to allow the production of petrol and diesel cars. If they did the same for steel, and it's a big if because it's a different problem, and said you shall not produce more than this amount of CO2 for a ton of steel, what's your best guess as to the technology route that you'd put your money in to actually arrive at a point where there's a significant reduction in the amount of CO2 produced?
Oh yeah, well, I guess you'd have to go for the direct reduction processes and produce hydrogen using a water electrolysis. With natural gas on standby, of course. So, but yeah, if it was mandated, then we'd still be buying our steel from iron and steel from China, maybe. I don't know, because they won't mandate that in China, I don't think. It is political, yeah. But that standard DRI technology is there now, and I was very surprised that BHP didn't use it in their HPI plant. I talked to one of their metallurgists who was doing the design, and he said they thought the fluid bed way was a great way to go. But the HPI operations had been operating for 20 years, and they could go and see them. You can buy 2 million tonne DRI plants off the shelf these days. Yeah. Sorry?
I was just going to ask one quick question before Martin does. You mentioned that grade is quite important, and the higher the grade, the more efficient the process. Yeah. How is the decline in iron ore grades going to affect steelmaking, and will there be an appetite for actual exploration for higher grade, smaller deposits of iron, such as magnetite, and things you're working on at the moment?
Well, I think you can see that now. Magnetite hasn't been a very popular source of iron ore. About 30% of the world's iron and steel is produced from magnetite. But magnetite you can get into much higher grades because it's easy to separate. It's a magnetic separator, and so long as you grind the stuff fine enough, then you can make high grades. So we've got 2 magnetite operations operating in West Australia now, and of course Savage River in Tasmania is still going at Grange, and FMG have put their money into Iron Bridge, more money than they thought they were going to put into it, but still they put money into it. And Iron Bridge is a magnetite deposit where they expect to get 67 to 68% iron grades from that. And there is a lot of magnetite iron ore around the Pilbara. The banded iron formation is a lot of it is magnetite. It goes from 20 to 30% magnetite. It's a really hard rock, so it takes a lot of energy to crush and grind it. So, but as you see from the pie chart, the processing is not a big issue. It's the iron and steel making that's the big issue. And so, yeah, Australia could move more into the magnetite area and is probably moving more into it. The Americans did it back in the 1950s. They ran out of hematite in the 1950s, and in Minnesota they established magnetite mines, and that's where most of their their iron comes from. The Chinese don't have any hematite resources. Most of their local iron ore is magnetite. So that's where the high grades could come from. Or we could do a better job of beneficiating our current hematite ores in that.
Yeah, apologies for fumbling my first question. Part of the problem is it's such a rich seminar that I had hundreds buzzing around in my head. So trying to arrive at one to ask you was a bit difficult. Yeah, quite. But apologies nonetheless. The other question I think it might be worth asking is, in the costing of all the different options, it's expected and understandable that the PV options come up very high. Is there any possibility, and you mentioned that part of the course problem with that is the capex, because once you've built it, it is kind of free, you know, not quite free, but it is very low, but with very large capex. Now, is there a possibility that the capex is being underestimated or even not included for some of the other options because we've already built it? Economically, that's kind of correct, but from the perspective of building a new smelter, perhaps the bars would look different. What do you think?
Yeah, it costs a lot to build a thermal coal-fired power station. Yeah, right. But it is a lot cheaper in terms of capital cost per megawatt hour, I would expect. I haven't done the calculations on that, but it would be interesting to do the calculations on that. Yeah, a gas-fired power station, of course, will be a lot cheaper because you just fire it into a jet engine and that's your energy generation. So your electricity generation. So it's the CSIRO would have taken that into account in their calculations, I'm sure. And they, if you read the report's done by ARENA, which is it was funded by ARENA, and CSIRO did the report. And if you can look it up on the web, it's pretty easy to find, and it will give you the basis of the capital cost estimate in there.
Thanks, I'll take a look.
Okay, well, if you can just join me with thanking Ray one more time. Thank you again.
Okay.